Hello everyone and welcome to a new video. In this video we will discuss how do we treat metals, the materials that exhibit many body effects, and in particular we would like to discuss the so-called embedded atom method, typically acronymed EAM, for metals. Remember, we spent some time discussing the failure of pair potentials in describing metals. And this, if you remember, this is attributed mainly that you need something to account for the many body effects in metals, and also the fact that if you remember, we said that as the number of neighbors increase, the cohesive energy doesn't go linearly as in pair potentials. If you remember, if you try to plot the number of neighbors, Z, and the cohesive energy, pair potentials usually give you some linear relationship, while, as we said, quantum mechanical calculations and also experiments suggest a nonlinear behavior, which is typically can be approximated as a square root z. Of course, it's not sharp as square root of z, but approximately. So we need some model to calculate energies that allows you to exhibit this nonlinearity. And that's actually the first successful attempt to do this, or one of the first. Let's not claim being the first. One of the first attempts is the embedded atom method. I think this is from the 80s, 1980s. So the energy based on the embedded atom method can be described in two terms. One of them is just simple pair potential. And really, you have flexibility in choosing this pair potential. It could be a Lennard-Jones. And to be honest, the main purpose for this pair potential is just for the hardcore repulsion. Really, that's what's needed from this component of the potential, the hardcore repulsion, which in Lennard-Jones, it's some constant over r to the power 12. So any function that can play the same role is sufficiently good. So that's one piece. The other piece is the many-body term, if you wish. So here we have something that represents the many-body effect. And how do we write it? It is a sum over all atoms. So this is a sum over all the atoms in the system of the sum functional of the electron density or the charge density of each atom, or at the location of each atom. So let's see, this is a summation of all over all atoms. That's to say, it's a sum over i's, starting from I equals 1 to n atoms. And what you do is you calculate the density, the electronic density or the charge density at this site, which is rho. So rho I is the electronic density at the site of atom I, right? And then you plug in this electronic density in some functional, right? Well, functional is really, I mean, it is, I mean, the concept of functional is like a function. The only difference is in functions, you plug in numbers, you get numbers. In functionals, you plug in a function instead of a function of a number, right? And you get eventually a number, right? So this is the electronic density at the site of the atom I. So that's rho I. Well, there is an ambiguity here. Do we do quantum mechanics here? Why do we have electrons in this kind of interatomic potential? Well, this is not really actual electrons. This is based on tabulations And let me clarify this. So how do you go over evaluating this many-body effect term? Suppose I have an atom I sitting here in this location in the space, right? And it is surrounded by some neighboring atoms. So let's say there is an atom here, 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 and so on and so forth. So each one of these atoms has an electronic cloud or electronic charge density surrounding it. Of course, I'm presenting it here in 1 dimensions, but of course it's a 3-dimensional object, so there is some electronic cloud for this atom. Similarly, this atom has some electronic cloud, and also this atom has some electronic cloud, and so on and so forth. And each one of them, like this one and this one and this one, they contribute something or part of their electronic cloud at the site I. Okay, so that's how you really calculate this density rho at each site. You calculate the distance between atom I and each one of the surrounding atoms. So this distance, let's do this with another color. You calculate this distance, this distance, this distance, and this distance, and this, and this. And then after that, based on the distance, you can tell how much electrons this atom contributing at site number I. So in a sense, you can say that if you are a mathematically oriented person, you can write this as rho I is a sum over all atoms J, provided that J do not equal I. That's to say, it's a sum over all the surrounding atoms. You calculate the distance between the two atoms in a vectorial fashion, Ri minus Rj, right? And then you plug in this distance in some expression for the charge density to know how much charge density exists at the location I. And typically, so this is F due to atom J. Typically, this Gaussian shaped charge density, it's an atomic charge density calculated previously using quantum mechanics. So in a sense, the embedded atom method is using quantum mechanical data. So there is a tabulated data for what should be the Gaussian, for example, that represents nickel, or what should be the Gaussian that represents iron, or that represents cobalt, or any other atom. And then by knowing the distance, the vectorial, the difference in the vector position of I and J, you can see what is the contribution of atom J to the site I of charge density. This way, you are capable of calculating the electronic density at site number I. Is that the end of the story? No. You plug in this electronic density for each atom I into some functional. And as we said, functional, where your input is not a number, instead it is a function, right? And you get a number as an output for that. So that's the functional F here, okay? So after you do this plugging, you get some contribution to the total energy. Of course, you repeat this exercise for each atom because, you know, I will do this assuming that this is atom I, and this is atom I, and this is atom I, and this is atom I. And for each atom in the crystal, I tell until I finish this calculation, okay? In a sense, and if you think about it, although this is really a many-body term, but its computation is not that expensive. It actually looks like what you do for two-body or pair potentials, because what you need to do is that for each atom I, you need to calculate the distance between that atom and the surrounding ones, the neighbors, the J's, right? And then after that, you know the charge density at that location, and then you do some plugin into this functional F. Okay, so in a sense, the many-body effect term is not computationally super expensive in comparison to bare potentials. It's just like similar, almost similar in its computational cost. Okay, now one last thing about this functional F. I have to say that there are many ways to write F, so let me do this in another page. The functional F in the embedded atom method, uh, There are some analytical formulas for that. We will not reproduce them here in this video. We can refer the interested person to the literature. In fact, we will discuss some of this literature in the exercises that we will take later. So there is some analytical formulas for equations where you plug in rho and you get the corresponding f of rho, which is eventually just an energy. It's an energy thing at the end, right? And for some embedded atom potentials, it's not analytical, it's actually tabulated. It's a tabulated function. Whether it's analytical or tabulated, it generally have this behavior. Like if you try to plot f of rho, which has, of course, units of energy, electron volt, for example, versus rho, which is a density, it has units of electron per some volume, let's say angstrom cube. The requirement is that F has to be decreasing, and convex. You know, it's decreasing and convex. So it's a decreasing function and it's a convex function. And you can really understand both of them quite easily. On one hand, as the density increases, that means that your atom I is surrounded by a lot of neighbors, right? Or that these neighbors are getting closer. It's one of those things, two things. It's either it's surrounded by too many neighbors or that the neighbors are very close to I, and that's why you have a large rho. But regardless whether it's because you have more neighbors or that your neighbors are at a short distance, indicating a strong bond, the energy should be lower, more negative, if you wish. So that means that there is more cohesion, right? So that's why it has to be decreasing. Decreasing means more neighbors. So if your neighbors increase, the cohesive energy has to become more negative. Or if the neighbor's distance of the distance with the neighbor, let's call it Rij, decreases, that means it's a strong chemical bond or a strong bond, then the cohesive energy also decreases. So that's why it has to be decreasing function. Why it has to be convex, that's actually a little bit subtle. Subtle because this convexity, and let me go back, it actually accounts for this nonlinearity in the cohesive energy versus the number of neighbors. And let me illustrate this. Let's go to the second page one more time. Look, if suppose your neighbors increased from 4 to 5. Remember, the increase of neighbors automatically is translated to increase in density. So that means, suppose you were at this density, so that's the corresponding energy. Suppose that this density corresponds to Z equal 4. I have to state carefully that Z is not rho. Z is the number of neighbors, and it's a discrete quantity, 4, 5, 6, 7, 8, and so on. While rho is an electronic density, and it's a continuous function. But suppose that this is the rho that represents tentatively 4 neighbors. Then if you go to 5 neighbors, which is here, there will be reduction in energy, gain in cohesion. Okay, let me call this delta 1. Now, on the other hand, let me represent this with a different color, maybe pink. So suppose your neighbor were 12 and they became 13. So on this graph, this will be here. Suppose Z equal 12 is here, and then it became 13. So I go down a little bit. So there will be another gain in cohesion or reduction in energy, which is this distance, which is delta 2. Obviously, the gain delta 1 or the amount or the magnitude of the reduction delta 1, as you can see here, is more in comparison to delta 2. I'm talking about the absolute magnitude. And that in a sense, let's go back, corresponds to this nonlinearity. In this nonlinearity, if I go from a small coordination to a larger coordination, then as you can see, there is a larger gain in cohesion. This could be the cohesive energy or the absolute of the cohesive energy if you want it to be a positive quantity. While if you go from a larger Z, let's say 12 to 13, then the gain is actually lesser. The gain is lesser. You see there is a gain here, which is larger. There is a gain here, but it is lesser. So it's nonlinearity thing, all right? That nonlinearity thing is reflected in this functional F. As we go to the next slide here, it is this convexity that's needed to represent the nonlinearity in cohesive energy versus neighbors versus Z. So you see, with this perfect or nice choice of F, you can, solve your problems that pair potentials couldn't actually account for. Now, if you go to a next page, we can say that with embedded atom method, you actually solve many problems. For example, you solve the problem of surface relaxation. Surface relaxation with embedded atom method is inward. And it's correct in comparison to pair potentials. You solve the problem of vacancy, formation, energy, where the ratio between the vacancy formation energy and the cohesive energy in an absolute sense is actually less than 1, around 0.3, and that's also correct in the embedded atom method. You actually solve Cauchy problem in mechanics, right? You don't get C12 equal to C44. That's the correct behavior, right? And depending, of course, on the quality of the embedded atom method potential, you can actually study phase transitions, something which you couldn't do with pair potentials. But you really need a high quality embedded atom method. Having said that, embedded atom methods are not perfect. For example, they do have a problem of their own problems in embedded atom methods. For example, that they are spherically symmetric. Symmetric. What that means is that if you have a central atom I here, and it's, let's say, surrounded by 4 atoms like this, the energy at site number I, which is, F of rho I, the embedding energy, that nonlinear term here, is exactly the same if, let's say, this is atom I here, and these two the neighboring atoms were like this. As long as the distances are the same. So if this is, let's say, I don't know, 2 angstrom, and this is 2 angstrom, and now this is also 2 angstrom, and this is 2 angstrom. Let's also make these 2 angstrom, and this is 2 angstrom. Okay, as long as these are the same distances, regardless of how these atoms are located in space, with respect to I, as long as they have the same pair distance, you will get the same F of rho I. And unfortunately, this is a problem, because in metals, we know this is not the case. Bring 1 iron here and surrounded by 4 iron like this versus 1 iron here surrounded by 4 irons like this, you will get a completely different energy, right? So this is a known problem, and it has been corrected in literature. Let's go with something called the modified embedded atom method, typically acronymed as MEME. MEME has its own successes. There is no warranty that it is always better, right? But it is a one way to get around this problem. We will stop here in terms of discussing metals versus covalent materials versus ionic materials. And I would like to mention something simple here, something called force fields, which is a family of interatomic potential for family of materials, where you have a set of interactions for every kind of pairs of atoms. For example, one of the important force fields for clays, it's called CLAYFF, clay force field. You can find about this in literature. This is particularly for clays and minerals and cements, right, and so on. This you have a tabulated interactions, let's say between calcium and oxygen, silicon and oxygen, calcium and hydrogen, and so on and so forth. Pretty much all the interactions that you need to represent clays and cements. When you have a family of interactions, this is called the force field. Other famous force fields, you have amber, you have CHARMM, and others. Of course, we are not trying to make a comprehensive list here. These are for biomaterials, biomolecules, not rather than biomaterials. I would say biomolecules. For example, for proteins, carbohydrates, nucleic acids, and so on. You have also one force field, REAXFF, reactive force field. It is supposed to do some chemical reactions, in a sense, do some sort of simplified quantum mechanics, if you wish. Originally developed for hydrocarbons, but it is also suitable now for oxides, for water, and many other families of materials as well. There is the universal force field. This is supposed to represent periodic table, tentatively, I would say. Of course, the broader the scope of the force field, usually the less accurate it is, right? If you have some force field focused on a family of materials, then usually it's better. And now, more recently, we do have these machine learning force fields. We are not really dedicating machine learning force fields. We are not really dedicating a whole discussion for it at this stage of the course, but they do exist now recently. I would say in the last 4 or 5 years, they do exist. They have their own pros and cons. We are not going to dedicate part for them at this stage of the course. We will leave this to a later part of the course. Let's summarize what we have covered today. Today we discussed how do we solve the problems of the nonlinearities, that the many-body effect that exists in metal. One way is to use the embedded atom method, where it's basically a bare potential coupled with some many-body term or a many-body effect term. The many-body effect term requires you to calculate the electronic density at the site of the atom. And don't worry, you're not going to do quantum mechanics here. You simply use tabulated atomic densities that has been calculated before. And by knowing the distance between each atom and your central atom and the atomic density, the electronic density of each one of these atoms, you can calculate the total electronic density at site number I. And then by knowing this electronic density, you plug it into some functional, you get the many-body effect contribution to the energy at site number I. One has to be careful about the functional F. It either has an analytical form or a tabulated form. Regardless whether it's analytical or tabulated, it has to be a decreasing function and it has to be convex, simply to represent this nonlinearity that we discussed before related to the cohesive energy. And what else? Then we said that EAM is not perfect. It has its own problem. Of course, it solved the key problems that we discussed, like Cauchy, vacancy formation energy, and surface relaxation. But of course, it has its own problems, like it's a spherically symmetric potential. And one way to rectify this is using the so-called modified embedded atom method. No warranty that they are better than EM or anything, but they give you some extra degree of freedom to fine-tune your force field or your interatomic potential. And then we summarize some of the important force fields in different families of materials. For clays and cements, you'd use CLAYFF typically. Of course, there are other force fields, so I'm not trying to advertise these or anything. Maybe these are the ones that I'm familiar with, but there are, of course, other good force fields for these families of materials, like CLAYFF, amber, and CHARMM for biomolecules, REAXFF for hydrocarbons and oxides. Universal force field is supposed to describe the whole periodic table, if you wish. And now we are living in the era of machine learning force fields. We will dedicate later part of this course for this family of force fields. Thank you so much and see you in another video.